understanding electric charge and forces boils down to a simple concept of particles either having a positive charge or a negative charge. And when you look at charge, you simply need to remember that opposites attract. Like charges repel and opposites attract. When you draw the field lines for a charged particle, you want to draw them in the direction that a positively charged proton would travel. So if you have a positively charged particle and you put another positively charged proton next to it, those particles are going to repel. Whereas if you put a positively charged proton next to something with a negative charge, the proton is going to move towards the negative charge. Those field lines represent the potential to exert a force. When two oppositely charged particles are near each other, their field lines are attracted to one another, and the field lines bend. Where the field lines are more concentrated, there is more potential to exert a force. If two particles have the same charge, if they're both positive or both negative, their field lines will repel one another, and you get these empty gaps where no force can be exerted. The forces and potential energy that we experience with charged particles are going to be very similar to the forces and energies we experience with gravitation. With the gravitational field, we calculate the force as the gravitational constant times mass 1 times mass 2 divided by their distance apart, squared. With charged particles, it's essentially the same equation, just with different variables. We have a constant k, and then we multiply that times charge 1 times charge 2 divided by the radius squared. When we talk about the force of gravity pulling something down to Earth, we multiply the mass of the object times the force of gravity to give us mg. When you're talking about a positively charged particle being pulled down to a negatively charged surface, you use the equation of charge times field strength. The charge is similar to the mass of the object, and the electric field, that's similar to the invisible force of gravity that's all around us. If you wanted to calculate the potential energy of an object in the air, we would simply write the mass times the gravity times how high the object is in the air. Likewise, with a charged particle in an electric field, we say the charge of the particle, that's similar to the mass, times the invisible force of the field times the distance, or how high the charged particle is above the surface. Since we know the force of a charged particle in an electric field is equal to the charge of the particle times the field strength, we can rewrite that equation to say the field strength is equal to the force exerted divided by the charge of the particle. We also know the force between two charges is equal to kqq over r squared. Combining these equations, you can simplify your equation for electric field to be the electrical constant k times the charge of the plate divided by the distance squared. Once you understand the basic concepts of an electric field and forces and charge and distance, the next step is to simply memorize a lot of equations. Here's a sample set of equations to memorize. There's even more equations to memorize in the handout sections on the website. To try and understand exactly where all these equations come from and exactly what they mean can be a little bit of overkill. At some point it becomes easier to just understand the basic fundamentals of how charge and force works, and then memorize the rest of the equations. This problem here is really nothing more than recognizing the appropriate equation to use. When you're talking about the force between two charged particles, the equation to use is the force of two charged particles is the electrical constant K times charge 1 times charge 2 divided by the radius squared. So if we double the distance, our new equation becomes KQQ divided by 2r parentheses squared, which is the same thing as KQQ divided by 4r squared. So we've reduced the total force by a factor of 4. In this case, we have a charged particle that starts at rest and then starts moving. There's really only two ways something at rest can start moving, and that is either a force is being applied to it, it can either have an outside force acting on it, or there can be a conversion from potential energy to kinetic energy. In this case, there is no outside force described, so we can assume there's a change from potential to kinetic energy. The equation for the potential energy between two charged particles is KQQ over r, the K being the electrical constant and Q being the two charges of the particles. We don't know K or Q, but we do know the distance between the two charged particles. Starts at 50 and goes to 100. In other words, the distance doubles. the new potential energy would be kQq over 2r. And since we've doubled the size of the denominator in our fraction, we've essentially cut our potential energy in half. Where did that potential energy go? Well, it went to kinetic energy, which is 1/2 times the mass of the particle times its velocity squared, which in this case is 1/2 times the mass times 20 meters per second squared, or 200 times the mass. We know this 200 m of kinetic energy is equal to half of the potential energy. That means the total initial potential energy in the system must have been equal to 400 times the mass. Now, when they're asking for the maximum velocity, what they're really asking is how fast is this particle going when all of the potential energy has been converted into kinetic energy. So you could write the final equation for kinetic energy to be 400 m is going to be equal to its kinetic energy, which is 1/2 times the mass times the velocity squared. If we do some math, the m's cancel out, multiply both sides by 2, and we get 800 is equal to velocity squared, and then square root both sides. You probably don't know the square root of 800, but we could break it down. The square root of 800 is equal to the square root of 8 times the square root of 100. The square root of 100 is 10, and the square root of 8 is going to be a little bit less than the square root of 9, or a little bit less than 3. So we could estimate the square root of 8 to be something like 2.8. So 2.8 times 10, our final velocity is roughly 28.